Hey everybody. Today we are going to do circles lesson number 2, and we are going to introduce a word that you might not be sure of, and that's going to be a chord. And I'm going to have you draw one right here. A chord is just a line that goes from one point of the circle to another. Now, the reason this is kind of different than usual is we're used to doing things like diameters or a radius. A chord is just from one point to another. It's not going to split the circle right down the middle necessarily. We're just talking about a line that goes from one spot to the other. And there's going to be some math involved with this. Now, in order to understand the math, we are going to bring in what we know about a diameter and a radius as well. So let's say the center of your circle is just going to be right about, let's put it right here. Okay. Now we know that a diameter or a radius goes through the center of the circle. So what we had right there that we drew was a chord. It did not go through the center, whereas a diameter or a radius would. So the line that we're going to draw right there, that would be an example of a diameter. And obviously, if we only took half of it, it would be the radius. Now, I do want you to notice something interesting about this diameter right here. Looks to me like it made a right angle. There is some significance there. So the first thing I want you to know is that if a diameter is perpendicular to a chord, then it bisects the chord, which means if it's perpendicular, these two pieces of your chord are going to be the same. Okay, so that's the first thing that I want you to know. All right, now piece number 2, and we'll get to this one later, chords that are equidistant from the center are also going to be congruent. So there's an example later on as you go through, let's see, I believe it's number 6 here, where you have two chords that are marked the same distance here from the center, as in right here. And again, we'll get to this problem in a second. This is sort of where common sense comes in. If it looks like it's going to be bisecting, it probably is. If it looks like it's going to be congruent, it probably is. Okay. Now, the third thing I want you to know, and this is going to come up a little bit later, intercepted arcs are the same measure as the central angle. Now, intercepted in this case would be, let's say we take a radius and another radius. And let's say this measure right here is, let's throw this out here. Let's say it's 57 degrees. That means the arc that it intercepts, as in the arc that is cut off by it, is also going to be 57 degrees. Now, you might not think this particular conversation fits in with chords, but it actually does, because when we get into a problem like number 7 right here, we have to consider, when we're trying to solve for x, we have to consider, well, if we have a 120-degree arc right here, then maybe, just maybe, it was created by a 120-degree central angle. Okay, so we are going to use this with chords. You just might not think it fits in right this second. All right, so we're going to go through and we're going to do not every problem, but we're going to do some of the problems together. And we're going to start with just finding the radius of the circle here. Now, I don't know if you noticed, but they didn't actually give you a radius of the circle. So we're going to have to create our own. So do we create it right here? Do we create it right here? What in the world are we going to do? Well, if you want to solve for something, then make a triangle. We've been doing this over and over again, so it makes sense. We're going to solve by making a triangle. And then because we have a perpendicular setup right here, so pretend, you don't have to draw this, but pretend that we have a diameter that is perpendicular to the chord. According to our rule, it bisects the chord, meaning I could take this and just call it 24 and then 24 more. So what I really have here is a right triangle, and if I want to solve for the radius, which would be that right there, the radius is really just the hypotenuse of that right triangle. So I could do 7 squared plus 24 squared equals c squared. Now, this is not always going to come out pretty. In this particular case, it does, but it does not always come out pretty. You can round it to a couple decimal places, whatever you want to do if it doesn't come out right. In this particular case, if you want to solve for c, you're going to take the square root of both sides. And you could have also called it r squared. It doesn't really matter what you call it so much as we know what we're doing here. So if 625 equals c squared or r squared, we're going to take the square root, and we're going to find out that that missing number is 25. Now, in this case, they gave you a label, so make sure you use it. 25 centimeters. All right, you can use that exact same idea on number 2. We are going to slide over to number 3 here. I'm planning on pretty much just doing the odd-numbered problems. Let's try that one more time and make sure we get it. So again, it said to find the radius. We don't have a radius, so we need to make one. This wouldn't be very helpful. This wouldn't be very helpful. But if we take what we have and we make a right triangle out of it, and we turn this into 4 and 4, then we could get our setup right. 3 squared plus 4 squared equals c squared. And I think a lot of us are at the point where we remember now that if it's a 3 and a 4 and you're looking for the hypotenuse, it's going to be 5. So that means in this case, the radius is 5 meters. So again, if it doesn't come out pleasantly, I know there are a couple on the back that might not, don't just assume that you did something wrong. It doesn't necessarily mean that. So for instance, when you get a problem like number 5, remember we're kind of bouncing around. So we did number 1, we did number 3. Let's do number 5. It's not going to always come out pretty. So let's be ready for that by doing problem number 5 here. Now this time they did draw a radius. It's not really going to help us much, but they did draw a radius. So what I want you to do is take that radius of 6, and I want you to swing it around and make a new radius. Now remember, no matter where you put the radius, it's going to be 6 no matter what, so you might as well just copy that over. And so if I want to know the missing side of this right triangle, which I'm just going to make blue right here, then I am going to say that 4 squared plus, and so one of the other things you need to know here is if we want to find the blue side, we are going to call that B. We're not missing C in this case, we're missing B. So 16 plus B squared equals 36. B squared equals 20. And then again, to find the actual B value, we are going to have to take the square root. Okay. Now, don't just write down that number. You know, B is 4.47, but that's not what they asked you for. They said solve for X. So if we know that this is 4.47, we have to go back to that rule that we talked about before. The chord was bisected. So this green part was bisected. It was broken up into 2 pieces, which means if we want to actually know x, we need to take what we got for that blue part and multiply it by 2. Now, just so we don't have any rounding issues, just leave that number in your calculator and hit times 2 while it's still there. And then it says round to the nearest tenth if necessary. So I will follow their directions and I will say x equals, and it was 8.94, nearest tenth would just be 8.9. They didn't give me any units, so if you're not sure, you can just call it U. It doesn't really matter. In this particular case, we'll just go with it. All right, let's do a couple of tricky ones here. In order to get number 7 right, you are going to have to remember what we learned back in the day about special triangles, and we have to combine it with what we just talked about. So remember, I gave you a rule at the very end when we were talking up at the top, when we were doing some definitions and some fill in the blanks, that if the intercepted arc is 120, that means the central angle is 120. Now, what is the significance of that? How in the world can we use that to solve for x? Well, I don't really know how to work with angles of 120. However, if we kind of take this picture and draw it again to the side, I could take 10 right there, and I could take my 120-degree angle, and I could chop it in half. Now, why would that be significant? Well, now I have a 60-degree angle up here, and that officially allows me to use the rules that I should know for 30, 60, 90 triangles. Now, in case you forgot, the rule behind a 30, 60, 90 triangle is that a 30, 60, 90 triangle is really just half of an equilateral triangle, which means this is going to be half of 10 right here. The shortest side is always half as big as the longest side because it really was just an equilateral triangle cut in half. So again, if you think back to that rule, if you don't remember that rule from the past, if you have a side of 8 on an equilateral triangle, and then you have another side of 8, and then you chop the equilateral triangle in half, well, then obviously what you're going to have is 4 and 4. So that's where that rule came from. That's why we're going to use it. Now, most of the class got this right as we were going on. Whenever you have a 5 and a 10, that middle side, you could use the Pythagorean theorem to solve for it, but really, we should remember the shortcut. And it's actually even going to be given to you on the reference sheet when you take your end of course exam. The pattern was, it's always whatever that little number is times the square root of 3. So 5 radical 3. So now if we go back to our original picture, we have 5 radical 3 over here. But remember, x was that entire length. So it's not just going to be from here to here. It's going to be double that amount. So it's not going to be 5 radical 3. It's going to be 10 radical 3. And again, we don't really have a unit here. So I'll just put units just to be safe. And we'll go from there. All right, last example of the day. By the way, number 8, we practiced this one before. This is sort of our trick question. This is one of those problems where we were maybe expecting something a little bit different. But remember, and if you don't remember the trick, you can just do a decimal for this one. Remember, a radius of a circle is the same no matter where it's at. So we're actually going to have an x down here as well. So there's your hint, but I was just going to do the odds today. So let's go on to this last one. We have a 5 and a 5. So how could we figure out x? Well, we talked about this here. We have a 90-degree angle right there. It's another one of our shortcuts. Now, this shortcut was called the 45-45-90 shortcut because whenever you have 2 of the same side, you also have 2 of the same angle. If you remember the shortcut, then you're done because you should remember the answer. This was the one that was 5 times the square root of 2. If you don't remember the shortcut, then I guess you have to watch for another 15 seconds. You have to do 5 squared plus 5 squared equals c squared. 25 plus 25 is 50. And then 50 is one of those radicals that you can break down really easily because 50 is really just 25 times 2. And the square root of 25 is 5. So that was the second shortcut. We learned it before. It will also be on the reference sheet when you take the EOC, but it's another good thing for you to learn. All right, I hope that gives you a jump start here in Circles lesson number 2. Thanks for watching, and I'll see you next time.